And welcome back to Geometry 2, a new chapter, Chapter 9. And we're starting in today with reflections. Pause the video, come back and check your work. And here we have the key. This should be so straightforward and simple for you, and I'm sure you have it. Today we're talking about identifying and drawing reflections in the coordinate plane. We'll be using the term isometry. So an isometry, speaking of isometries, is a transformation that does not change the shape or size of a figure. It's like isolated figure. No change in the shape or size, no dilation. Reflections are isometries. Translations, slides, are isometries. And rotations are all isometries. Isometries are also called congruence transformations or rigid motions. I like that term, rigid motions. It feels like something is not moving, very rigid, right? Congruence transformations is another great term. Congruence meaning the same, right? Congruent, equal in size and shape. So we can call isometries congruence transformations or rigid motions. Recall that a reflection is a transformation that moves a figure, the pre-image, by flipping it across a line. The reflected figure is called the image. A reflection is an isometry. So the image is always congruent to the pre-image. Tell whether each transformation below appears to be a reflection and explain. So figures A. Let's say the pre-image is blue, the image is red. Is this a reflection? Is there a way we could draw a line and show that each point from A is equidistant to that line in image B, or the red image, right? And you can see it is not. It doesn't appear to be flipped, does it? If you were going to give this a transformation, you would probably call this a translation, like it's been slid over. Okay, and how about in the figures here in part B? Does it look like we could draw a line of reflection? And it sure looks like that, doesn't it? We could draw a line right down, vertical line down the center, and the image appears to be flipped across that line. You can go to pages 50 through 55. Why don't you pause and go there for a moment and look at the basic transformations that we did in the very first chapter. Okay, so on page 50 you can see a reflection, a rotation, and a translation. And if you just kind of make your way to 55, you can see some of the work that we did with those transformations, which are all isometry or congruence transformations, right? Rigid transformations. So tell whether each figure here appears to be a reflection. And does figure A? And it's a little deceptive, but no, it is not a reflection. Notice this arm of the star is longer than this arm, right? So not a reflection. How about here? And the answer is yes. Appears to be reflected across a line that would be drawn between the two here, like almost a little steeper than a 45-degree angle maybe, right? Okay, draw a segment from each vertex of the pre-image to the corresponding vertex of the image. Your construction should show that the line of reflection is the perpendicular bisector of every segment connecting a point and its image. Okay, so here we have a line of reflection, and here's a point and its image, right? And so we can see that there is a perpendicular line, bisector, or this line of reflection bisects the segment that joins the point and its image. So a reflection is a transformation across a line. This is called a line of reflection, so that the line of reflection is the perpendicular bisector of each segment joining each point in its image. So point A is the same distance from the line as A prime, right? If we look back here and we drew a line here, we could see that this lower corner is the same distance from the line as this lower corner, right? Or the peak of this half circle is the same distance from the line of reflection as the peak of the image, right? Good. Okay. So we are going to copy the triangle and the line of reflection and draw the reflection of the triangle across the line. Why don't you go ahead and try that here? You're going to have to pause and, or actually, yeah, pause and use the figure that you have in your notes. Okay, so we want a vertex that is the same distance from the line of reflection as this vertex, right? Same with this vertex, the same distance from the line of reflection out here, and finally the third, and then you can just join the vertices, right? So you can measure the distance from each vertex to the line and then measure across the same distance from the line on the opposite side of it, right? So here we have those 3 vertices, the points for them given. And then we would just connect the images of the vertices. So hopefully you did this already in the first slide on step 1. So go ahead and take a look at how this quadrilateral has been reflected across the line of reflection here. And again, the easiest way to do that is to take the vertices of the pre-image and reflect the vertices across your line of reflection. Draw all those vertices, and then you can just draw the segments between the vertices. Okay? Here's a problem-solving application. 2 buildings are located at A and B. They are to be connected to the same point on the water line. Where should they connect so that the least amount of pipe will be used? Okay, so we're trying to locate a point X on the water line so that AX plus XB has the least possible value. So a strategy that we can use is to reflect point B across the water line. We know that the shortest distance from B to the water line is a perpendicular segment, right? So let's reflect point B across the water line and locate a B prime point opposite it. So when we do that, for any point X on the water line, any point here will be the same distance from B as it is from B prime, right? So if I choose a point here, then B is the same distance from that point as the reflected point B over there, right? And so we could say that AX plus XB, let's look at it this way, AX plus XB is the same as AX plus XB prime. This is the same, right? So AX plus XB prime is least when we get AX and B prime to be on the same line. AX and B prime to be on the same line, right? Because the shortest distance between any 2 points is a straight line. So we're basically taking this point and imagining that it's on the opposite side and creating a straight line between A and B. It's just that it's not A and B, it's A and B prime. Keep in mind though, B to X is the same as B prime to X. So the shortest distance between A and B is A to B prime. Isn't that cool? So this is how we have identified point X. It is the intersection of the water line when we draw segment AB. Okay, so to verify your answer, you could choose several possible locations for X and measure the total length of the pipe for each location, which we're not going to do now, but you could confirm that this is true, and you would find indeed this is the point that is giving us the smallest value. And the question again was, let's go back and look, where should they connect the pipe so that the least amount of pipe will be used? And there it is, at point X, okay? So let's look at this question, a similar question. If A and B were the same distance from the river, what would be true about AX and BX? Well, if A and B are the same perpendicular distance from the river, then AX and BX would be congruent. I guess this is given that X is a midpoint between A and B, right? Got to have that info too. So let's look at the math behind reflections. We've already used this earlier in the text, but across the x-axis, if we reflect a point, what which piece of the ordered pair, which coordinate are we taking the opposite of? And of course, it's the y value, right? We're taking the opposite of the y, which reflects us across the x-axis. If we want to reflect across the y-axis, we're taking the opposite of x, right? That flips us across the y-axis. So there's a bit of an irony there that we're flipping, or we're changing the opposite lettered coordinate, right? We're changing x to negative x, and that flips us across the y-axis, okay? But it makes total sense, doesn't it? If we want to reflect across the parent linear equation, y equals slope of 1x plus 0, right? This is our parent equation with a 45-degree angle. Then we would simply switch xy becomes yx, and we have now reflected across y equals x, the parent linear equation, which is kind of cool. Imagine this. Imagine this point here is at 2, 4. 2, 4, and now look at its reflected image is at 4, 2. It helps to use real numbers, doesn't it? Okay, so let's draw reflections in the coordinate plane. Let's reflect this figure across the given line. So we're asked to reflect this across the x-axis. X-axis means we're going to change the y values all to their opposites, right? So you could make a little table, and we're going to say x prime becomes 2, positive 1, right? Y prime becomes positive 3y value, and z prime is negative 2. So if we graph each, go ahead and do that. Come back and check. You should see interesting reflection across the x-axis. Very cool. And we have a reflection now across the parent linear equation, y equals x. So to do this, again, we go from xy to an image that is yx. So negative 2, 2 becomes 2, negative 2. 5, 0, 0, 5. And t is at 3, negative 1 becomes negative 1, 3. Go ahead and graph them. Come back and check. And you should have, get rid of this, you should have this. Interesting reflection. Black is the pre-image and red is the image across our parent linear, which is really cool. Okay, try one more across the x-axis and come back and check your work. A nice basic reflection, and it's just across the x-axis, right? Really straightforward. Let's take a look at your lesson quiz. Does this transformation appear to be a reflection? Your answer is yes. And draw the reflection across this line of reflection. Pause, draw that, use your vertices, right? Reflect the vertices, and you should now have that beautiful reflection. And finally, reflect the figure with the given vertices across the given line. So we're reflecting on the parent, across the y, and across the x. Come back and check when you have written down your coordinates. And in number 3, number 4, and number 5. All right, good. Go have fun reflecting.